Hello everyone, this is Vijay Kumar Purohit, Assistant Professor in the Department of Chemical Engineering from B.V. Raju Institute of Technology, Narsapur. Today I am going to discuss about the course called Chemical Process Calculation. It is the subject related to chemical engineering, and in the chemical process calculation we will discuss about the topic called material balance calculations. So what is material balance? A material balance is also known as mass balance in the systems. As you know, in chemical engineering, we have different unit operation and unit process. And each unit operation in unit process, we can consider as one system. So whatever the amount of material that is entering in the system and whatever the material that is exit out the system, that balance we should know. And that study is called as material balance calculations. So it is generally about consider the amount of mass that is entering and amount of mass that is outgoing to the system. So it depends on this material balance calculation depends on the law of conservation of mass. So suppose let us consider we have a system. That system may be either a unit operation where only physical changes occur, or a unit process where both physical and chemical changes is occurring in the system. So, in material balance, whatever the amount of material that is incoming, that comes under input. Input is nothing but the mass of material entering the system. And whatever after the processing, the material will be processed within the system. After processing, the material will go out of the system. That material amount is called as output material. So, it comes under output. Output means the mass of material leaving the system. So, in a system, there will be some mass that is entering, and the mass after it will be getting processed. After the processing, the mass will, the product or the processed material will go out, and the total amount is called as output. So now we understand in a system we will have the mass input, and after processing the product or the unreacted material or unprocessed material, whatever will go out, that is called output materials. So apart from that, suppose that system will real systems or a system will processing unideally, then what will happen? Whatever the input material we are sending to the system, some material will be accumulated within the system. Okay, those materials also in the material balance we have to consider those amount also to take care of the material balance. So that comes under accumulation. Accumulation is the mass of material accumulated in the system. So whatever the mass, it will be accumulated within the system during the processing. That is called under accumulation. For example, suppose I put 100 kg of input materials. Okay, while processing, there may be some 10 kg of material. Some 10 kg of material will be remain or accumulated within the system during processing. And the output will get only 90 kg. Okay, so that's why, as you can consider, this 10 kg is accumulated within the system. And to consider the total mass balance, we should also consider what is the accumulated amount. So, okay. So next point is called under generation and consumption. These two concepts, generation and consumption, will comes under the concept when we will have some reaction within the system. Just now examples whatever I gave, some amount is input and some amount is accumulated, and the remaining amount goes out of the system. In this process, it called as a unit operation, where no reaction is happening. But if the system is a unit process, if it is a unit process, then inside the system some reaction will be happen. Okay, some reaction will be happen. The reaction, what is the reaction? The reactant will give rise to product. Okay, so during that process we can find whenever there is some reaction, there will be some amount generated and some amount consumed. So when there is some unit, in case of unit process, we have to consider these two terms, the amount of material generated and amount of material consumed. So these are the 5 key terms we need to consider while evaluating the material balance. Those are input, amount of material getting input, output, amount of material leaving the system, accumulation, if any amount is accumulated within the system during the processing, and the other two terms are generation and consumption. Those will be considered while in the system when some reaction is happening, or the unit process type of system, in which due to the reaction some amount will be generated and some amount will consume. Those also we have to take care while considering the material balance. So why this material balance is important? So with the study of material balance, we can calculate what is the amount of product from the system, the amount of unreacted reactant leaving the system. We can qualify the mass losses, how much mass is getting lost, and we can able to calculate the mass of material required for the process. Suppose this is the system, we give some input and some output will be there. So by doing this mass material balance calculation, we can idea about what is the amount of product that may be formed, what is the amount of in the output, whatever the unreacted or unprocessed material is there, and we can calculate about the amount of material accumulated or that amount of material that the loss happened to the system in terms of material, and what is the amount of material required. Suppose we need 100 kg of product. So by considering the unreacted or unprocessed product and amount of the loss, what is the amount of input that we should give, that also we can able to calculate by using this material balance calculation. Apart from that, it will give us the overall feasibility and efficiency of the system, and it will help us in calculating the detect or any faults present in the system. And whenever we will design a new process or new system, and we have to consider this material balance calculations. These are the all key points why material balance calculation is important. So let's come to what is material balance. As I discussed, it is based on law of conservation of mass. It is nothing but the total mass in the system must be remain constant. Okay, whatever the input we are giving. Okay, suppose 100 kg input we are giving. What is happening to the 100 kg? Where it is going? Some material will go to product, some material will be accumulated, some material will evaporate, some material will consumed during reaction, and some extra material will generate. So whatever the total mass is there, that we have to taking care, unless there is a mass transfer across the system. Okay, so within the system the mass should be constant. There the net inflow of mass should be equal to net outflow of mass. Okay, within the system. So the material balance calculation we have to use two approaches for doing material balance calculations. Those are total material balance and component material balance. We will discuss one by one. So what is total? First point is, what is total material balance? It states that the total mass of all element entering in the system must be equal to total mass of all the material leaving the system. Suppose we have a system. Let us consider we have a system, whether it is a unit operation or a unit process. So total mass, what is the total mass? Okay, suppose this is the system, and here let's suppose say input I am giving 3 input A, input B and input C. 3 materials I am entering. Suppose A is X kg, B is Y kg and C is Z kg. Okay, suppose I have 3 material A, B, C. All 3 are entering as input with respective weights X kg, Y kg, Z kg. So this is our system. Okay, so according to total material balance, whatever the total input, it should be equal to the total output. It means what? In output, whatever we will get, the total kg should be X plus Y plus Z. This is called total material balance. In total material balance, we will check the overall amount entering and overall amount leaving the system. Okay, just for that we discuss, the total mass into the unit or system should be equal to total mass out of the unit, or we can, in equation form, we can write input should be equal to output. Okay, and here this one we can consider under one assumption or condition. The system should work in a steady state process and where accumulation is zero, accumulation and no chemical reaction is happening, or we can say it is a unit operation. It is a unit operation where no chemical reaction is there. Okay, it is a steady state process, means input rate is equal to output rate, or sorry, the properties or flow rates are not changing with respect to time, and accumulation is zero. Accumulation zero means there is no loss inside the system. Okay, in that case we can assume, we can say the total material balance will be input is equal to output, and it will be generally called as a, it will be a ideal condition. Okay, but generally we found the systems are not ideal. So in the unit operations where there is no chemical reaction is happening, there will be some amount that will be accumulated. It will be obvious. When we put 100 kg of total input, we may not get total 100 kg after the output, because some amount will be accumulated within the system. So that we also have to take into account while considering the total material balance. So what we can do, so we can revise the total material balance as input is equal to output plus accumulation. So whatever input we give, okay, some amount will be accumulated with the system and some amount will be go as a product or output. So the total amount of input should be equal to the output plus accumulation, and this will be valid where there is no chemical reaction, or we can say for unit operations. Okay. So what if there is a chemical reaction? Now suppose consider this is our system, this is our input and this is our output, and as we discussed, we will have some accumulation within the system, or we can say that is the loss of the material. Okay, so input will be equal to output plus accumulation when there is no chemical reaction is happening. Now consider, suppose some reaction is happening. So reaction, some reactant will give rise to product. So what will happen? So the reactants in the reaction, the reactant will consume, the mass of the reactant will decrease. In the same time, the mass of the product will increase based on their mole basis. So those two terms, the amount of mass consumed and the amount of mass generated, those things we have to consider if it is a, if any chemical reaction is happening within the system. Now the material balance is changed to input is equal to total input is equal to total amount of material generated in the reaction. Okay, total amount of material accumulated within the system, total amount of material goes out, and total amount of consumed material consumed during the reaction. These two terms, generation and consumption, it will be considered when there is a chemical reaction, because as I discussed, in case of chemical reaction, the reactant will consumed, the reactant mass will decrease and the product mass will increase. That is, some generation, some consumption and some generation will happen. That's why we need to consider these 2 points. If there is no reaction, then we will have input is equal to accumulation plus output. So this is all about total material balance. Now let us discuss about component material balance. Let us draw the same diagram. Suppose this is system, the total input, this is the output. According to overall material balance, we have total input, total amount of input should be equal to total amount of output. This is equal to total, this is under total material balance. Now we will discuss about component material balance. What is component material balance? It states that the mass of each component entering must be equal to mass of each component leaving. In total, what is the difference? In total material balance, we will take consideration of the total mass entering and total mass going out. But in component material balance, we will consider about each components. What is the, suppose one component is there, how much component is getting entering the system, and that component how much amount is leaving the system. We will consider only about the components input amount and output amount. That called as component material balance. Just for example, suppose say input will give three components A, B, C. Three components are there. So in output also, if there is no chemical reaction, suppose say some unit operation. So we are having some unit operation. Okay, there is no chemical reaction. Then output also we may get A, B, C. Suppose there is no chemical reaction. Input is A, B, C. Output is A, B, C. Okay. Suppose A is X kg, B is Y kg, and C is Z kg. Okay. These three amount we entered. Okay. So what should be the, so we do some operation. Suppose say A we got P kg, B will got Q kg, and C will get R kg. Okay. Let us consider like this. A, B, C three component with X, Y, Z kg respectively is entering, and in the output we get ABC of P, Q, R kg, some different weight. Okay. Then according to overall material balance, we will have input is equal to output. It means what? X plus Y plus Z. It is what? Total amount of material input, total amount is equal to P plus Q plus R. P plus Q plus R is equal to nothing but total amount of output product. Total input should be equal to total output on the steady state when there is no chemical reaction. Now, component balance. In component balance, we will consider about the material balance of component. The material balance component means what? The amount of material A that is entering should be equal to the amount of material A that is leaving. The amount of material B that is entering should be equal to the amount of B that is leaving. The amount of material C that is entering is equal to the amount of material C that is leaving. Okay. While we will solve a numerical, that time you are able to understand more clearly, and you can differentiate between what is overall material balance and what is component material balance. As I discussed, in component material balance, we will discuss about only components. So the input of only component A should be equal to the output of only component A. Or if some accumulation is there, then, or some reaction is there, then we will consider for component A only the total amount of A in input, total amount of A in output equal to total amount of A in the accumulation. Okay. In component material balance, we will consider about only component A. Similarly, for when some reaction is happening, total A input, total A generated, total A in the output, total A accumulation, and total A consumed. Okay. This is all about component balance, where we will discuss about the amount of material of specific component, not overall amount. So let us discuss one numerical, then we can to understand much more better about this concept of material balance. So one example is present in the screen. So let us the waste acid from a nitrating process containing 20% HNO3, 55% H2SO4 and 25% H2O by weight is to be concentrated by addition of concentrated H2SO4 containing 95% H2SO4 and concentrated HNO3 containing 90% HNO3 to get the desired mixed acid containing 26% HNO3 and 60% H2SO4. Calculate the quantities of waste and concentrated acids required for 100 kg of desired mixed acid. So this is the question. So to solve this type of question, this question is related to material balance calculation. First thing what we have to do is we have to draw a block diagram of the question. In the block diagram, whatever in the question information data is given, we try to incorporate those data into the block diagram. Okay, so from the question we can able to know that, we can guess it. This question is related to some mixing unit operation. This question is related to some mixing unit operation, where some streams are, as the input is coming, it is mixing, it is getting mixed, and we got some product. So let us draw the block diagram. Let us consider this is my mixing unit. We will draw the block diagram only. This is the mixing unit. Okay. Then one by one we will try to provide the information to this block diagram. So first line, the waste acid from a nitrating process industry, nitrating process containing 20% HNO3, 55% H2SO4 and 25% H2O by weight is to be concentrated, okay, by addition. This, okay, we have some input from the waste acid, okay, which composition is this one, okay. We have some output from output of waste acid from the nitrating process industry, whose composition having that waste acid is having 20% HNO3, 55% H2SO4 and 25% H2O. We need to concentrate this. How? We need to be concentrated by addition of H2SO4 having concentration, addition of concentrated H2SO4 containing 95% H2SO4 and concentration H2NO3 contain 90% HNO3. It means what? We have a stream of waste acid from the nitrating process industry having this composition 20% HNO3, 55% H2SO4 and 25% H2O. We need to concentrate this acid by mixing two streams. First is concentrated H2SO4 having 95% H2SO4 and another stream having concentrated HNO3 having 90% HNO3. Okay, you understand? So we have one waste stream. We have to concentrate those waste stream by adding two concentrated H2SO4 and another concentrated HNO3 stream to get the desired product of this composition. Okay, so let us draw the diagram. So first is our input to the mixing unit is our waste acid. Okay, what is its composition? The composition is 20% HNO3, 55% H2SO4 and 25% H2O. Okay. So let us calculate the total percentage, how much it is. 55, 20, okay. It is coming around 100%. Okay. The total percent is 100%. Okay. So we can, all the component is mentioned as the total percent is 100%, and this is all our weight percent as in the question given. These are all representing weight percentage. Okay. Next is we'll add some to concentrate this waste acid. We need to add concentrated H2SO4 stream. What is its composition? It contains 95% H2SO4. Okay, this is H2SO4 stream. This is the H2SO4 stream. Another stream we have to add. That is what? That is HNO3 streams having 90% HNO3. Okay, you can consider this total stream is 100%. It means all the component of the stream is given. But here in the concentrated H2SO4 and concentrated HNO3, the total is not 100%. It means something is missing. What is that thing? When it comes concentrated H2SO4, 95% H2SO4, what about the next 5%? Generally, the 5% will be water. Okay, we should know these things. That acid is generally mixture of H2SO4 acid is generally mixture of pure H2SO4 and water. So similarly like HNO3 acid mixture, 90% in that stream 90% HNO3 is there. It means we have 10% on the next 10% is water. By default, it will come because acid mixture means it is a mixture of water only by default. Okay. So these three are input things. Okay, and we got some product. Let us consider product as output stream. Input means incoming stream, output means product stream. So what is the product stream? 26% HNO3, 60% H2SO4. This is the product stream. So as you can say 60 plus 26, it is not coming 100. So there is just some missing data. What is that missing? As per the given data, we can able to see there are three components: HNO3, H2SO4 and water. So the percentage of water data is not given in the question. We can assume the total mixture is always 100% by weight. So 2 is given. So third one is 100 minus 60 minus 26, and it will come around. It will come under 14%. Okay. Again, next data is there. Calculate the quantity of waste acid and concentrated acid required. We have to calculate the quantities. Let us consider the total feed, okay, of concentrated acid is F1 kg. Total weight is F1 kg. In F1 kg, you have 20% HNO3, this thing. Let us consider this is F2 kg, total amount. And this is called F3 kg. Okay. So this F1, F2 and F3 is the total amount of total quantities of waste acid and concentrated acid to get 100 kg of desired mixture. Desired mixture means P. And the P is already given. The P is 1000 kg. Okay. This is what given in the ask. And what we have to calculate? We have to calculate what is F1, the amount of material, what is F1, F2 and F3. Okay. So I draw this diagram in the better way. You can see the feed stream 1, which is having total kg is F1 kg, having this composition by weight percentage. Feed stream 2, H2SO4 stream is having this composition where 95% is H2SO4, 5% is water. So there is no HNO3 stream. Why I mention means we have three components. So let us describe all the components percent in all streams for each of our calculations. Similarly, for HNO3 streams, the total amount is F3 kg. Okay, and this is the composition: 90% HNO3, 10% H2SO4, and 10% H2O, and no H2SO4 means 0% H2SO4. The product stream, it is total is 1000 kg is given. We need to produce that one. So having this composition HNO3, H2SO4 and water 14%. So in the question what we have to calculate is what is the amount of F1, what is the amount of F2, what is the amount of F3 in terms of kg to produce 1000 kg of this product mixture. Okay. So this problem you can see only the information of mass in and mass out is given with some composition. So this problem comes under mass balance or material balance calculations. So for that we need to get two approach. One is overall material balance, another is component material balance. Let us do. First one is overall material balance. As overall material balance, we know we should consider the total material input is equal to total material output. From the question we can see F1 is the total material in, F2 is the total material of, and F3 is the total material of concentrated acids and for feed material, and P is the total material that is going out. So according to overall material balance, we will have F1 plus F2 plus F3 will be equal to P. The P data is given. The P is nothing but 1000 kg. Okay. So this will let us consider this is equation number 1, where overall materials, total material balance, total material is F1, this is F2 and this is F3 is giving the P. So the total material in is equal to total material out. The P is given 1000 kg. Okay, so this is, let us consider. We need to calculate what is F1, F2, F3. That is our statement according to statement of the numerical. Okay. So this is overall material balance. Then we consider about component material balance. As we know that in each stream we have three components. One is HNO3, one is H2SO4, another is H2O. So first we will go for HNO3 stream. In HNO3 stream, what we will do? What is the amount of HNO3 in feed 1, amount of HNO3 in feed 2 plus amount of HNO3 in feed 3 is equal to the amount of HNO3 in the product. This is called component material balance of HNO3. Amount of HNO3 in feed plus amount of HNO3 in F2 plus amount of HNO3 in F3 is equal to amount of HNO3 in product. Similarly for H2SO4 and water. We will do one by one. So component material balance for HNO3. So as you can see this diagram, let us go for this diagram. You can see how much HNO3 is there in feed stream. It is given 20%. 20% of what? HNO3 is present here, 20% of F1 kg. F1 is the total kg. Out of total kg, 20% is HNO3. Here, how many HNO3 is there? Here, HNO3 is present 0% of F2 kg. Here, HNO3 is present 90% of F3 kg. And here, HNO3 is present 26% of 1000 kg. Okay. So that is the component balance. Okay. So let us do that one. So as you can see, so F1 20% of HNO3 that is in feed 1, in feed 2 0% of HNO3 in feed 2 and 90% of HNO3 in feed 3 is equal to 26% of HNO3 in the product, that is 1000 kg. So 20% means 20 by 100, like 0 by 100, 90 by 100, 26 by 100. Okay, and we will get 20 by 100. We can simplify it at 0.2 into F1 plus 0 into F2 plus 0.9 into F3 is equal to this 0.26 into 1000. Okay, this is called component balance of HNO3. Okay, this let us consider this is equation 2. Equation 1 is overall material balance. Equation 2 is component material balance of HNO3. Similarly, component material balance of H2SO4. As you can see from this diagram, H2SO4, here we will have 55% of F1, H2SO4 here 95% of F2 and 0% of F3 is equal to 60% of 1000 kg. Okay, let us write the same thing for H2SO4. Yeah, 55% of F1, 95% of F2, 0% of F3 is equal to 60% of 1000 kg. Okay, so when we will simplify, we will get 0.55 into F1 plus 0.95 into F2 plus 0.0 into F3 is equal to 0.6 into 1000. This calls equation 3. Similarly, another component there are three components. First one is HNO3, H2SO4, then water. Similarly, we did for H2O unit also, where we have 25% of water in feed 1, 5% of water in feed 2, 10% of water in feed 3 and 14% of water in product. That comes under equation 4. Okay. So what is the equation we got? First equation we got the overall material balance, where F1 plus F2 plus F3 is equal to 1000. Okay. Then we go for three component balance. In each component balance we got one equation. So total equation we got 4. In this 4 equation, how much variables we have? As you can see, we have 3 variables. 4 equations, 3 variables. What are the variables? Variables are F1, F2, F3. So that is what we have to calculate. What is F1, F2, F3? The amount of materials entering. Okay. That is our objective to calculate. Okay. So as you know that to solve this type of equation, when 3 variables are there, we need only 3 equations. Okay, that will be sufficient for us. But we generate 4 equations. So what we can do is, we can take any 3 equations from these 4 equations, to solve or to get F1, F2, F3. Okay. So let us consider I took these three equations. Okay. So how to solve this equation? As you can say, these are the linear equation. Okay. So we can solve directly by using the scientific calculators. Okay. Calculator, or many solving techniques are there. We can go for the numerical approach to solve this type of equation, or the general approach is there. We can convert it into matrix form. So this is the normal equation, linear equations are there. If I convert to matrix forms, I can get 0.2, 0, 0.9, 0.5, 0.95, 0, 0.25, 0.05, 0.1 into F1, F2, F3, these are the variables, is equal to 260, 600, 140. Okay. As you know, this is the matrix representation of this equation. We can represent it as AX is equal to B. Okay. That is the linear form of linear equation in the matrix form. Then we can solve it any form like X is equal to A inverse B, or any other approach is there, or better we have scientific calculator is allowed, by where that to solve this type of equation, the facilities is there. Very quickly we can calculate and we can get F1, F2, F3. The F1 and F2, F3 while solving we can get F1 will come 400, F2 will come 400 and F3 will come 200. Okay, this is our answer. What is F1? The amount of waste acid, the amount of concentrated H2SO4, the amount of concentrated HNO3 required. Okay, so overall what we calculate is on mixing of. Okay, so what is the desired? The question is we have to produce this one. Okay, we have to produce 1000 kg of the product with having this composition. Okay, and we have three streams. This stream, waste acid stream, concentrated H2SO4, concentrated H2SO4, concentrated H3NO3. The question is how much quantity of the feed stream of individual F1, F2, F3 we should add so that in the feed we will get 1000 kg amount with exact proportion. Okay, that we solved. After solving we can get is, if we take 400 kg of waste acid with this composition and we will mix them with 400 kg of concentrated H2SO4 with this composition plus 200 kg of concentrated H3NO3 with this composition, when we mix them, exactly we will get 1000 kg with this percentage. Okay. So this is what we solved, the one numerical as an example of material balance calculation, and that example is related to mixing unit and it is related to unit operation, as we know, unit operation, where there is no generation, no consumption of material is happening. So generally we consider then unit input is equal to output plus accumulation. But in solving this numerical, generally we will consider this is a ideal and steady state process. Then accumulation also we consider 0, and that approach of input is equal to total output we apply to solve this equation, and we take two approaches. One is total input is equal to total output, and the component balance. The component of each component input is equal to the mass of each component input is equal to mass of each component out. By taking these two approaches, that is the material balance, we solve this numericals. Okay. So thank you. This is all about that material balance calculations theory and one example. In the next classes, we will solve for the material balance calculation for many other unit operations. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.